Hi guys, this is the session about limits, and remember that this presentation is available on Canvas. Okay, so let's begin with the concept of a limit. Okay, so we have two classical problems. That is, how do you calculate the tangent and the velocity of anything? Okay. The tangent problem, what is a tangent? If you recall from geometry, the tangent is a line that touches a certain curve, okay? Usually it's a circle, but it can be any curve. So tangent comes from Latin, from tangens, that means to touch, okay? So you can imagine a line that barely touches a certain curve and then goes on its own way. Okay, but how can we talk about this in a more precise manner? For a circle, well, it's very straightforward. No, we have a circle like this, and if you draw a tangent, it's a line that just touches the circle, but it doesn't cross from one side to the other. So it looks okay. But what about if we don't have a circle, if we add something more elaborate? Well, in this case, um, we have a curve and we have a tangent line on the point P. But as you can see, this line doesn't touch the curve just in one point. It touches in 2 points. So is this a tangent or not? Well, it looks like this is what we would mean by a tangent, no? But in this case, if we define it as the line that only intersects in one point, well, it doesn't match the definition, okay? So what are we going to do? Maybe we don't care so much of the other point of the curve, of what happens over there, but we only want to know what happens near the point P, okay? So let's see, how would we work this out to find a tangent at a point P of a parabola? Okay, so this parabola y equals to x squared. How do you picture this? Well, we would draw a parabola like this, right? So this is the parabola, and this point over here is the point 1, point 1. And the tangent line would be this red line that we have over here. That is the line that we want to get. So what do we do to start approximating this tangent? Because we don't know exactly what this tangent is like. So we have a point Q that is on the parabola. That's why it has the coordinates x and x squared. And you can use the value of x that you like. It can be 5 or 3, whatever, okay? So it will be a point that is on this parabola. And the blue line is a line that connects point Q with point P. Okay, so what do you think that we are going to try to do? Since this is a secant, what happens if I start to putting these 2 points together more and more and more and more. So it looks like it's going to be more similar to the tangent line, right? To the red line. Uh, so what we need to do is to find the slope of this blue line. Okay, so how do you find the slope for 2 points? If you recall from analytic geometry, um, to get the slope between 2 points, you have to find the difference between the y values divided over the difference of the x values, okay? So in this case, the difference of the y values is going to be x squared minus 1, because this is the y coordinate of the upper point, and this is the y coordinate of the down point. And here we have x minus 1. Okay, so this is going to be the slope for any point that we wish to use. Let's use x equal to 1.5. So that yields 1.5 squared is going to be 2.25. So now we calculate the slope. So make sure that you get this calculation and you get a slope of 2.5. So that means that it is an approximation of the slope of the tangent, okay? So now let's try for different points, for different values of x. So we're going to choose for 2, for 1.5, for 1.1, 1.01, 1.001. And we're going to get these values for the slope, okay? So you can work it out by yourselves. And you'll notice that you are getting every time closer to this value. Now, what if we use values of x that are below 1? So we can use 0, 0.5, 0.9, 0.99, 0.9999. Okay? So also the value of the slope seems to be closer to the number 2 every time, okay? But why don't we use the x value of 1? So what is going to be the problem there? If we use the value of x equal to 1, both points are going to be the same point, okay? So when you do this, this calculation for the slope, what are you going to get? You're going to get 0, you're going to get 1 minus 1 equals 0, and 1 minus 1 equals 0. So you get 0 over 0. And what's the value of 0 over 0? That's right. 0 over 0 is not defined, because it can be anything. So remember, 0 over 0 means that there is a number, then when you multiply it by 0, it gives you 0. Okay, so which number could be that? Well, it could be any number. Okay, so the value of 0 over 0 is not defined. Okay, so that's why we don't use it. So as we are doing this process of getting close, but without touching the x value of 1, what we say is as we are doing a limit. We are trying to get the limits as the point Q approaches the point P of this slope. Or another way is the limit as x goes to 1 of this quantity, okay? X squared minus 1 over x minus 1. So we say that this is the limit of the value, okay? So now that if we wish to get the slope of the tangent, well, we could say, well, it turns out that it is 2. So by using the point slope equation of a line, if you recall from analytic geometry, the formula is this, okay? So we already have the slope m equals 2, x1 and y1. We can substitute the values of p. So it's going to be x minus 1 equal to 2 times x minus 1. Or if we clear dy, we get this value for the equation of the tangent. Okay? So this is what we did on this approach. We go approaching q to p until the blue line is every time more similar to the red line. Okay, so this is a nice way to get the tangent. And it doesn't matter if we use a value of q that is over here. We also can get the value of the tangent. Okay, so that's the way that we are going to get the tangent. Now, for the case of velocity, um, if any object like a falling body, imagine a ball that is falling down. Um, does it fall at the same speed all the time? Well, the answer is no. It starts by a velocity equal to 0, and then it accelerates, and it goes faster and faster and faster and faster. Okay, so maybe to watch it in a in a falling object in free fall is a little bit hard to visualize. But for example, if you have also a ball that falls through a slope, you will notice that the ball at the first moves very slowly, and then it gets a faster speed. Okay. So what is the velocity of that object? So let's say that we drop a ball from a very large tower. And the thing is that we cannot find the instantaneous velocity at every moment, no? So which we want to know exactly, for example, at 5 seconds after we threw the ball, what is the velocity of the ball, okay? So we can take some sort of an average velocity, okay? So what we could do is that we can take a video of the ball, right? And what is a video? A video is a succession of fixed images, okay? So it's a lot of photographs that are taken within a certain time interval, okay? So let's say that we measure the position of the ball at second 5, and then one 1 decimal of a second later, 1/10 of a second later. Okay. So the average velocity is going to be how much the ball moves divided between the time it took for it to move. Okay. So let's say that This is how it moves. Well, here we use a physics formula about the square of the time. 4.9 is related to the gravitational acceleration divided over 2, and we get this speed. Okay, so is that the speed of the ball at the time number 5 seconds? Well, the answer is that is not exactly that, but if we take a time interval each time more close to 5 seconds, what we're going to get is a different average velocity, but it tends to a certain value. In this case, what is the value that you think it's going to be similar to? It looks like it's going to 49, right? So if we do this process with a time interval every time more closer and closer and closer, we're going to get to the real instantaneous velocity, okay? So which is going to be 49 meters per second. Okay, so what we're doing in this case is taking the limits of a function, okay? So what is the limit of a function? Okay, you see, we found that a function uh, gives us a set of values. It can be a function like this, x minus 1 over x squared minus 1. Okay, so the problem is that if we substitute x equal to 1, we get 0 and 0, so it's not okay. But we can make a table for values below 1 of x and over 1 of x. So what are we going to get for the value of the function? In this case, when we are getting values below 1, we see that we start to get values that tend to 0.5. And if we take values of x that go near to 1 from the upper side, we also get values of 0.5, okay? So even though the function is not defined on x equal to 1, the value of the function looks like it tends to a certain value, okay? So if we make a graph of this function, what we see is the following. It looks like this, okay? But notice that just in the value of x equal to 1, there is a hole here because the function is not defined in this place, okay? But as we can see, we are approaching a certain value coming from the left and coming from the right. That's going to be the limit of the function as x approaches 1. So what we say is the following. No? That idea is that the limit when x approaches 1 of x minus 1 over x squared minus 1 is 0.5, okay? So that's how that's what we're trying to state. Even though this function doesn't have a defined value for x equal to 1. But the thing is that we get close, get close, get close, get close. And every time we're getting closer to this value. Okay? So we say that the limit of the function, the limit of f of x as x approaches to a is equal to L. Okay? So that's the way we define that. Okay? So that is the definition that we are going to work with. There is a more mathematically rigorous definition of this, but that goes beyond the scope of this course, okay? So, but notice that it's not just substituting the value directly, no? We have to get closer and closer and closer every time. Okay? Because, for example, we can have different functions. If you notice, these look similar, but they are different functions, okay? What is the nuance about this? Well, let's see. Both have I mean, the three of them have this blue line. They follow the same blue line, but what happens at the point A? Okay, in the first function, the point A is just a part of the curve, and it's like any other point. In the function B, we have removed that point, so the function is not defined on A. Okay. In the third case, we all removed the point from the curve, but we added this point over here. Okay. So the function is defined on A, but the value is different from or is far away from the curve. Okay. So in these cases, in both of three cases, the values of f are different. And in one of them, it's not even defined, okay? However, the limit is the same in the tree because as we get closer to a from both sides of this function, we get to the same value, okay? So the three functions have the same limits in a, okay? Even though they are not the same function. Okay, let's see, for example, guess the value of the limit when x tends to 0 of sine of x over x. Okay? So the sine of x over x is going to be, if we try to make a direct substitution, we get 0 over 0. Okay? So that is undefined. But how can we approximate this value by the limit? So what we're going to do is that we're going to get values of x closer to 0, but that they're not actually 0, okay? And remember, when we use the function like this, the sine of x, the x value is assumed that it is given in radians, okay? Because if we use degrees, we're not going to get the limit correct, okay? So let's see this table, okay? So we can notice that because the sine and x are both odd functions, when you divide an odd function between an odd functions, you get an even function. Remember that we saw the even and odd functions? So what does that mean? That it has the same value if we use a positive or a negative value of x, okay? So you can do this on your calculator. And what you're going to do to see is that we approach 0.999999 as we approach 0 on the value for x, okay? So we can say that the limit of this function when x goes to 0 is 1, okay? Now, uh, what are the one-sided limits? As you see, we have to approach a function from both sides. So what are we going to do? We're going to approach them first from one side and then from another side. That's going to be a one-sided limit. Okay, consider this function. This is called the Heaviside function, okay? Heaviside is the last name of a person, okay? It's not, it doesn't mean that that there is a side that is very heavy, okay? So what is this function? This is a very basic function. It just says, if you give me a value of t below zero, I'm going to give you a zero, okay? But if you pass the value of zero, if you give me a positive value, then I'm going to give you a number one, okay? So it's like when you deliver something on time, okay? So if you deliver it before the deadline, um, that means okay, no? The zero value means you are okay within the deadline, no? But if you deliver it past the deadline, like for example, a payment of some credit cards, for example, then if you pay past that deadline, you activate some value, no? It can be a penalization for late payment, okay? So now the question is, what is the limit of this function when t goes to zero? Well, it depends. If you come from the negative values, you're approaching all the time zero. So the limit is going to be zero. But if you approach from the positive values, you're going to get one. So these limits are different if you come from the left or if you come from the right. Okay, so when we put this like t tends to zero minus or t tends to zero plus, that is the meaning that we are approaching from the left side or from the negatives or from the positive side, okay? From the right side. That is the meaning of this. Okay, another way to write it is like the limit of f of x when x tends to a from the left is L, no? And similarly, when we are talking about a right-hand limit, we say that the limit of f of x as x approaches to a plus is L, okay? So those are the one-sided limits. Okay, so let's say that we are approaching the value of f of a from the left. That means that we are using only the values that are less than a, okay? And if we are approaching from the right, we use the values of x that are bigger than a, larger than a, okay? Okay, so what happens? What does this mean then? The limit of x of f of x when x goes to a? That means that the right hand limit and the left hand limit go to the same place, okay? That is what we mean when we talk about the absolute limit of a function, okay? let's say, for example, notice this graph. So which are the limits of this? So we have the limit of g of x as x tends to 2 from the left, the limit of g of x as x tends to 2 from the right, the absolute limit of g of x as x tends to 2, and the same limits, but when x tends to 5. Okay, so I invite you to write down what your answers are, and we'll see if you're correct. Okay? So let's see if we got everything right. Okay. So notice that, for example, the value of the function, is it defined on 2? It's not. It has 2 holes here. Okay? And the value of the function is defined on 5. It is defined on 5. Okay? But we have here these like gaps. Okay, so if you study the graph, you will notice that when x tends to 2 from the left, the limit is going to be number 3. But if you come from the right, it's below that, it's going to be equal to 1. Okay? So the question is, are these two limits the same? The answer is obviously not. So because they are not the same, then the limit, the absolute limit of g of x as x tends to 2 doesn't exist. Okay? There is no limit of the function there. Even though the limits, the one-sided limits do exist, okay? Because these do exist. Now, for x equal to 5, the situation is a little bit different. Because when x tends to 5 from the left, this is equal to 2. And from the right, it's equal to 2. Okay? So both limits in this case are the same. So the limit, the absolute limit of g of x as x tends to 5 is 2. Okay? And notice that the actual value of the function is not 2. It's something different. But it's no problem. There's no problem with that. How can a limit fail to exist? Okay, so we have one question there, no? So if both limits don't reach the same, the limit doesn't exist, okay? Now let's see, for example, what about this limit? Sine of pi over x. So remember, pi is a constant. Um, but what happens with this as x approaches 0? Okay, if we use a value of x each time more similar to 0, we can notice that f1 is 0, f of 1/3 is 0, of 0.1 is going to be 0, and for values of 1/2, 1/4, we also get 0, okay? So it looks like this is going to be 0, right? But wait. The thing is that the values that we selected for x in this case are not appropriate. Okay, so we sometimes can make a wrong guess if we don't take if we're not careful with the values that we use. Okay, because in reality, if n is any integer number, this is going to be zero. But if we use any other value of x, of n, then we are going to get something else. Okay? So that's one thing. And the other is that we see that as we reach zero, this thing is like giving a lot of movement, no? Like a lot of oscillations. So what's going to be the limit from the right or from the left? Okay, so it turns out that it is not defined, okay? So the limit doesn't exist, not even from one side or from other side, okay? So be careful. Now, we have limits that can be infinite. So what does that mean? Um, when we arrive to a value of a function that starts growing and growing and growing and growing, that's what we call an infinite limit, okay? So the value of the limit is, or we say that the value of the limit is infinite, okay? So that is what we mean. So in this case, mm, does this limit exist? Well, we're going to say that although the limit is infinite, this infinite is not a real number, remember. Infinite is not a number. There is no number that is called infinity because infinity doesn't obey the rules for numbers, okay? So infinite is not a number. Okay, but this is one way to say that the value of f of x is going to be unbounded, okay? Or is going to grow as large as it wants. So we can have functions like this, where when x equals to a, the value of the function is not defined because we don't know what is the value exactly here. But what we can see is that it goes approaching infinity, okay? So this red line is what we call an asymptote, okay? An asymptote is a line, a straight line that is associated with a curve, in this case, this function, but they never touch. They get close however you like, but they never touch, okay? That is an asymptote. Okay, and what happens if it goes to a negative value? If every time it is more negative, more negative, more negative. Okay, so then it's going to be we're going to say that the limit of the function is minus infinity. Okay, so it can happen, and notice that is not the same. So in this case, we say that the limit of the function is negative infinity. Okay, or it decreases without bound as possibly as x approaches to a. Okay? Let's see, for example, the limit of minus 1 over x squared when x tends to 0. What's this going to be? Um, if you notice, it is going to have a graph that goes down all the time, no? Because as x tends to 0, this is going to be a very large number, and 1 divided over a very large number is going to be a very, sorry, this is going to be a small number, and 1 divided over a small number is a very large number. And because it has a negative value, it's going to be minus infinity. Now, can we talk about infinite limits one-sided? Yes, of course. We can have limits from the left or from the right, plus or minus infinity. In fact, we have a lot of functions that arise naturally that have different limits, different infinite limits as one approaches to a value. Okay? So these are the four cases. A function that approaches infinity as x tends to a from the left. A function that approaches infinity as as x approaches x from the right. A function that approaches minus infinity as x tends to a from the left, and a limit that is equal to minus infinity as x goes to a from the right side. Okay? And okay, I already mentioned that the line for the value of a is called a vertical asymptote, and we're going to call it a vertical asymptote if any any of the following is true. Okay, so it doesn't matter if we have a function that comes from one side and doesn't have an infinite limit. If from one of the sides has an infinite limit, then we have a vertical asymptote. Now, for example, for the vertical asymptotes of the tangent function, remember that the tangent is sine over cosine, okay? And we are going to probably have something vertical asymptotes when the value of the cosine goes to 0, okay? Because that is when when functions go to infinity. Okay, and when does the cosine function has values of 0? Well, it turns out that every time we have an angle of uh, pi halves, okay? So, in those cases, what is the value of the sine? Well, the value of the sine is going to be 1. Okay, so we have 1 over 0. Well, that's not defined, but if we take values closer to that, we're going to get, it depends. So if we come from the left, we have a positive infinite, but if we come from the right, it's going to have a negative infinite, okay? And this happens over here, over pi over 2. But the same thing happens if we add or subtract from this value half a cycle of a circle, no? That is a value of pi, okay? So every pi um, repetitions, we have a vertical asymptote, okay? And notice that it goes to minus infinity from one side and to plus infinity from the other side, okay? So very well. Now, the limits have certain laws as well as numbers because usually limits are, except for the infinite limits, limits when they exist, they yield a number, okay? So what can we do? We can add limits, we can subtract limits, we can multiply limits by a number, by a constant. We can multiply limits with themselves, and we can divide limits, okay? So in those cases, it's the same as adding numbers, no? So if we add limits, it's going to be the addition of the functions that yield the limit, no? So if we have a function that is the sum of two functions, it's going to be the sum of the limits. For subtraction, the same. For multiplying by a constant, is going to be the same. When we multiply, we have a function that is multiplying. The limits are multiplications. And notice when we are using a division, what is going to be the only problem? If the limit of g, which is dividing, is 0, okay? If that limit is 0, then we have to do other things, okay? Okay, so these are the verbal ways to describe these laws. And that's it. So what happens when we have this example, for example? We have two functions here, the blue function and the red function. Okay, so by using these laws, we can state that the limits are going to be what? So try to do it by yourselves. All right. If you want, you can pause the video. Okay, so let's see what we got here. So the first one, the limit of a plus b. If you see the graph, you will notice that those limits as x tends to minus 2 of x and g are 1 and minus 1. Okay? So the limit of g is minus 1, and the limit of f is 2. Okay? No, sorry, 1. So we just add the limits and notice that this 5 is going to multiply the limit of g, okay? So in the end, we get the result of minus 4. Okay, now for the second part. So what happens with the limit of this times this? Well, when x tends to 1 on f, what's the limit here? Well, it can be seen that it is 2. But what is the limit of g? Well, we have to calculate the limit from the left and from the right. But notice the following. The limit from the left is not the same as the limit from the right. So this limit is not defined. And if it is not defined, then I cannot multiply this. So this limit doesn't exist. Okay? All right. Now for the value of x as it tends to 2, well, we can estimate the value of f as 1.4, and for g is clearly 0. Okay? But if we are doing f over g and g is 0, in that point, the limit also doesn't exist. Okay? Because the denominator is 0. Okay, and we also, what happens when we have exponents or roots? Well, they are some sort of an application of the multiplication rule. For example, f squared is just f times f. Okay, so we obtain the following. Okay, and well, the thing with these limits is that the n has to be a positive integer. Okay, and when taking the square roots, just remember that if you take a square root or any root with a value of n that is even, you cannot take that if the value of f is negative. Okay. Okay. So okay, these are cases also for just when we are doing x tending to a, which we can use, no? But it's just the same. Okay, we can evaluate limits by direct substitution, simply substituting the value, except when uh, when we have 0 on the denominator and the numerator. Hmm? So if we have 0 over 0 when we do a direct substitution, what we can do is that we can make a factorization. Okay, so notice that if you have x squared minus 1 over x minus 1, the upper side is a difference of squares. So it can be factored as x minus 1 times x plus 1. And notice what is going to happen. X times 1 over x times 1, what's it going to yield? It's going to yield 1, okay? And so since they have a common factor, it cancels out. And now we can do a direct substitution of the limit, okay? But this is when taking limits, okay? We can do this with the to get the value of the function. Okay, but because that value is not defined, but only when we are getting limits, we can do this cancellation to um, to see what is going on. Okay, so the limit is going to be 2. So in general, if both limits are the same, if both functions are the same, the limits are also the same. Okay. When using one-sided limits, we can apply the same, and sometimes it's easier to get the left-handed the left side limits or the right side limit. Okay, and if both are the same, then we have our limit. Okay, so remember, for example, what is the limit of x um of the absolute value of x as x tends to 0? So if you recall, it was a graph like a V. And what do we have here? Um, well, since this is a piecewise defined function and exactly the point where it changes the definition is in 0, we are going to use simply the definition. Okay, so we can take the limit from the left and from the right. Okay, and both limits are the limit of x as x tends to 0 from the right is 0. And the limit of x of negative x as x tends to 0 from the left is going to be also 0. Since both limits are 0, then the result is that the limit exists and it is 0. Okay? We have also the squeeze theorem. That means that if we have a function and we can squeeze it between two functions that we know, we can get the limit of that. Okay? So it states the following. If I have a function that is less or equal when approaching a certain limit, a certain value, then the limit is also going to be below that, okay? Less or equal. So what happens if I have two functions? One is over the other, and the other is over other, okay? So they are squeezing. So then, if the limit of the upper function and the limit of the down function go to the same place, then the function that goes in between has to go to the same limit, okay? So we can see it like this. So you notice here that the red line is being squeezed between the green line and the blue line, okay? So that is the idea of the squeeze theorem. If the limits of h and f exist and they tend to this, then uh, and g is always um, less or equal to h and f is less or equal to g, then this happens, okay? So let's see, for example, we have this kind of limit x squared over sine over 1 over x. So notice that we cannot evaluate this with the law of multiplication of limits, because what is the sine of 1 over x? It doesn't exist. Okay, so this means that this limit doesn't exist? Well, no, actually the limit is defined because of what is doing the x squared here. Okay, so in this case, that is a little bit a funny case. We can use the squeeze theorem. Okay, so how are we going to do it? So first, notice that what is the value of the sine of 1 over x? Or where is it going to be always? It is always going to be bounded by -1 and 1, because the sine function does this, okay? It always oscillates between -1 and 1. So it's always on that range. Okay, so we are going to use that to find the functions that we want to use to squeeze this. Okay. So now, if we have something that is between 0 and 1 multiplied by x squared, um, what are the upper and lower bounds of this? So they are going to be x squared times 1 and x squared times -1, okay? So these are this green function and the blue function is x squared and minus x squared, okay? So these functions bound the red function, which is x squared times sine of 1 over x. Okay, so it turns out that if they are bounded, then what is the limit of this function and what is the limit of this function as x tends to 0? It's 0. Since these functions are bounding the functions that we are interested in, then the conclusion is that if these limits are the same, then it's going to be the same limit, okay? So the limit of this is going to be 0, okay? So these limits are 0. Therefore, the limit of x squared of sine of 1 over x is also going to be 0. Very well. Now, we're going to see the part of continuity. What is continuity? In general terms, we can say that the continuity of a function or a function that is continuous is a function that can be traced with a pen without taking the pen away from the paper, okay? So it's a line or a curve that can be followed continuously with no gaps. So what we say is that if we want to know if a function is continuous in one place, the definition that it is continuous is if the limit of the function is the same as the value of the function. Okay? In A. So what does this mean? It means that that both of these things have to exist and be the same. Okay. So f of a is defined. Okay, there is no gap, there is no strange thing, no asymptote, nothing. Okay. The limit has to exist. Mhm. And then the limit and the value of the function have to be the same. Okay. So it makes sense, right? Okay, so if any of this is not applied, if any of these conditions are not met, then we have a discontinuity there, for example. Okay, so for example, the displacement of a vehicle is a continuous function of time. Okay, because there is nothing that can teletransport from one place to another. No, it has to travel through that distance. Um, but for example, there are discontinuities, for example, in electric current. An electric current can be applied and then it suddenly goes down, no? In a not continuous way. Okay, so another way to understand this is as a function that you can draw with a pen without lifting the pen from the paper, okay? So evidently, this is a discontinuous function, right? Okay, so there are places where it is continuous. Yes. For example, in this region before x equal to 1, we can see clearly that this is continuous. But in these places, there are discontinuities. Okay? So is it continuous at x equal to 1? No, it's not continuous. Why? What is missing here? The limit exists, the limit of x equal to 1 equals to 1. Yes, but the function is not defined. Okay, so that's how we know that it is not continuous. All right, what about this point, x equal to 3? Is it continuous on 3? No. Why? The function is defined at 3? Yes, it is defined. Its value is this. But what is the limit? The limit does not exist because it has a limit from the left side and a limit from the right side, but they are not the same. So the limit doesn't exist. So the equation is not continuous. Okay, what about number 5? Does the limit exist? Yes. Is the function defined on x equal to 5? Yes, of course. We have its value here. Is the limit and the value of the function the same? No, sadly not. So this doesn't work. Okay, so this is the explanation I gave. Okay, so I want you to try to see if these functions are continuous or not continuous. So where can you look for discontinuities? Okay, this is the um, option D. This is the step function. Okay, so it's the function that goes from stairs. Or what it does is that you get the integer value of x. Okay, So, well, I want to invite you to try to explore this on your own. You can look for the in the presentations for the answer. Okay. All right. So, and what kind of continuities do we have? We have removable discontinuities like this. They are discontinuities that it's only one piece of the function. Okay, so there's no problem. No, like you can take one point away from the function, or you could cover that discontinuity with just putting one point into it. Okay, so that is the continuity of that is the way to describe a removable discontinuity. Okay. In this case, we have an infinite discontinuity because it goes to infinity. Okay. And when we have something that uh, takes a step, this is a jump discontinuity. Okay. So, okay. So functions can be continuous from the left or from the right. What is going to be the way that we know if it is continued from the left or the right? Because remember, we asked if the limit exists and if the function is defined, okay? So if the limit, maybe the limit, the general limit, the absolute limit doesn't exist. But if the limit from the left exists and it is the value is known, the value is defined, and they are the same, then it is continuous from the left, and the same from the right side. Okay, so maybe there's a discontinuity, but uh, if we only take the right side or the left side of the function at that point, then we have a continuity from the left or continuity from the right. Okay, and a function can be continuous in a given interval. What does it mean? That for every value on the interval, the function is continuous. Okay. Well, the properties of continuous functions are similar to the limits. No, when we add continuous functions, the result is a continuous function. When we subtract continuous functions, the result is a continuous function. When we multiply continuous functions, the result is a continuous function. And when we divide continuous functions, the result is going to be continuous as long as g is not equal to 0, okay? In that case, we're going to probably have a discontinuity, okay? Okay, so if we take functions that are, for example, sums or divisions, well, they're going to be continuous. So any polynomial, because it is made out of continuous functions, in this case, the continuous function is x, then every polynomial is going to be always continuous, okay? And what is a rational function? A polynomial divided over polynomial. In that case, both are continuous, but maybe the polynomial on the denominator, if it has a value of 0, then it is not continuous. But as long as it is not valued for 0, it is continuous, okay? So, for example, these functions, the volume of a sphere over here is continuous, okay? Because this is a constant, and R is continuous, okay? This function that gives us the height of a ball thrown in a certain direction is also continuous, okay? All right. So let's move on. Okay. So what is the limit of this? Okay, do we have to make a factorization of this and this? No, not necessarily. Okay. Why? Because they are asking us for the limit when x goes to -2. Okay. So since this function is rational, we just have to make sure that the denominator is not 0. Okay. Maybe the numerator is 0. That's not a problem. But if the denominator is 0, then there is a problem. Okay. So all we have to do is substitute. And by direct substitution, we get that the limit is -1/11. Okay? So no problem with that. So a lot of functions are continuous. The ones that we use and love the most. For example, sines or cosines are continuous. But for example, the tangent, is it continuous everywhere? It is not continuous at certain values, okay? So, for example, we have the tangent here. And we already explored the asymptotes of the tangent, okay? So that is where the function is not continuous, okay? So, these functions are continuous in every number under domain, okay? Polynomials, trigonometric functions, exponential functions, rationals, roots, inverse trigonometric functions, and logarithms, okay? All these kinds of functions are continuous. And also, the composition of functions is continuous, okay? So, and if we have two functions, f and g, that are continuous at a given point, then the composition is going to be continuous, okay? So, I'm going to stop it over here. So that's it for this session. And I will be at reach at my email for any questions, okay? So thank you very much. Have a great day.